Okay, so we are done with the principal component analysis. And so this today we'll start a new topic. So we step into the realm of unsupervised learning. And actually for principal component analysis, PCA, I think it also falls into a an unsupervised learning to that field because um, the PCA doesn't require like the data points to be labeled with explicit labels to each data points. It's just analyze the features alone. So the PCA only relies on the features, and it's basically a examination on linear combinations of the original features, and it tries to uh, extract the most informative informative dimensions, and those most informative dimensions like PC1, PC2, PCK, they are just in nature they're just a bunch of linear combinations of the original features. Okay, so and in when we study word embedding, the properties of word embeddings, for example, we need to um, use our dimension reduction technique like PCA to to reduce the dimensions to 2 dimensions or 3 dimensions, and then we can visualize the word vectors uh, to represent to demonstrate the relationship between different words that are semantically uh, nearby or semantically apart from each other. And PCA is often used in combination with the clustering algorithms that we're gonna talk about today, because clustering algorithms is also a unsupervised learning technique, and it helps to extract the unobserved or hidden features among the data by basically grouping similar data points into the same cluster, and so that we can observe the patterns by looking at the groups resulting from the clustering algorithms. And it also does not rely on the labels on the data. So the data can be unlabeled data, can be raw data points, and the algorithm will just use the uh, by observing the distance between the data points and use that distance metric to put similar data points, or at least the data points that the algorithm considers similar, to be in the same group. So yeah, and let's look at the outline. So basically, we will talk about K-means, hierarchical clustering, and density-based clustering first, because speaking from the from the perspective of methodology, these the first 3 types, they kind of assigns the discrete labels, or assign the discrete clusters to the data points. And the last type of clustering method, which is called the mixture Gaussian model, and the expectation maximization method, EM method, is something that we will cover in the next lecture, because it basically uses very different um, philosophy about how clusters should be assigned to each data points. And it's actually the continuous labels that one data point can belong to multiple clusters, but with different probabilities. And anyway, let's start from K-means, and then hopefully we can cover the first 3 types of clusters in the lecture today. And I will also release the homework for both K-means and the PCA, um, the principal component analysis, and that will be the last programming assignments for this semester. Okay, so let's get started with K-means. So again, a little bit background. So so far we have talked about a lot about the learning problems in supervised learning realm. And in supervised learning, we know that each data is given a correct label for each data point in the training set. So in unsupervised learning case, we actually don't know the label. And the so-called unsupervised learning is actually to discover the patterns or the structures in existing data. Like if our data can group into two clusters, then we can probably conclude with pretty good confidence saying that, okay, there are two generic categories in our existing data. So the clustering algorithms is the goal is to find clusters in data. So given the two clusters, two groups, how do we design an algorithm that can automatically find this pattern for us? Okay, so in a real world clustering example, actually Google uses the clustering algorithms on text data, like given the news reports articles uh, um, that are published in a day, then it's a huge amount of text data. Then how do we efficiently cluster cluster them into different categories is a is a very challenging issue actually. And nowadays I don't think unsupervised clustering alone it's enough, because now we have more sophisticated neural network based text classifiers. So we can actually train very accurate text classifiers, which is based on supervised learning technique, so that the newly published articles can be uh, classified into any existing categories. Okay, but text clustering is also, I think it's still important because um, there are new genres of texts coming out every day, new types of writing, new types of articles, new types of fictional, non-fictional writings, creative writings. So uh, running a unsupervised clustering algorithm will be helpful to for the algorithm for the computer to discover unobserved types or unobserved clusters, which are still meaningful. And applied to computer vision, the clustering algorithm can be used to segment different parts in the image. So like the pixel points that are of similar colors will be aggregated into the same clusters um, automatically by the algorithm. And this is kind of similar to the uh, object detection uh, algorithm that are popular nowadays. But the most recent state-of-the-art object detection actually relies on well-trained convolutional neural network-based models, and that the data that helps training those CNN or ConvNet-based models are manually labeled. But the image segmentation, like like the pixel clustering based method, is also a very good supplement to the manually labeled data, because it can helps identify the unobserved patterns, unobserved objects, or unobserved um, patterns in the data sets. Okay, my PowerPoint shows it's yeah, right, it's okay now. Okay. Anyway, so after the backgrounds, now let's look into the K-means clustering algorithm first. And it's a pretty classical algorithm. It's first proposed in 1960s, 1950s. So this algorithm, what it does, so first of all, the K in this in its name, K means the K is the number of clusters. So one of its characteristics is that we need to decide K first. So this K is needs to be arbitrarily selected or needs to be pre-selected. So for example, we determine that we want to cluster the existing data sets into two clusters, right? Now our goal is to find the two clusters, okay? So our first step, because we don't have any information available yet, so we can pick two random points as the initial cluster centroids. So the word centroids is for stands for the center of a cluster. Okay, so it's just a terminology, but the same meaning as the center. So we can pick two random points, and then the second step is critical. It will paint the data points that are closer to the red centroid to be red, and those that are closer to the blue centroid to be blue, right? We have two centroid data points. One is red and one is blue. So according to the distance, we can always set a hard threshold. Whenever a data point is closer to red, we will paint it red. And whenever it's blue, we paint it blue. So we can separate all the data points in our existing data sets like this. We can do a hard separation because for any data points, it can always be either closer to red or either close to blue. Okay, now is the third step. In step 3, we will update the positions of the centroids. So this time the new red centroid will be the average of all the current red points, right? Because we have painted so many data points to be red on the right, right? Also meant to be red, and so many others, the second half to be the blue color. So we can use the average x and y coordinates in this 2D dimension space as the new candidate, as the new positions for the new red and blue centroids, right? So after, for example, after the updates, the centroid will move to a new position because the majority of the blue data points is up here. So after the centroid is updated, we will probably see that the new centroid will move upwards and the new red points will move downwards. Okay, so that is one circle, one cycle done, or one iteration done. So we will now, what we will do is to repeat the step 2 and step 3. So we will now paint the data points again because the centroids are at different positions. Now the distance from those centroids can be recalculated, right? So previously, for example, the points, for example, these points, it's closer to the old red centroid, but maybe at this step, it's closer to the blue centroid. And maybe it also holds for these centroid positions, right? For these data points, they are now closer to the blue centroids. And those data points that are closer to the old blue centroid, they now is apparently closer to the red one. So the color needs to be updated. So we need to repeat the step 2 by repaint all the data points after we recalculate all the distances. Okay, so after the color, after those data points are recolored, right? Notice the difference here are recolored. Then step 3 will be processed because the centroids needs to be updated. Anyway, let's repeat these processes until the positions of the centroids no longer change, or until no more points need to be repainted. And that is the step where we stop. And also we call that this algorithm now converged to a stable state. And the colors assigned to each data points are no longer need to be changed. Okay, so now the resulting colored patterns is the clustering results. So we can conclude that, okay, all the data points up here, they belong to the first cluster indicated by the blue color, and all the data points at the lower left bottom, they belong to the second red cluster. Okay, so these animation shows a complete process of running k-means. Okay, so let's use some formulas to describe the algorithm more formally. So because we're used to use the data points, lowercase x and y's, x to indicate the data points, and we use the superscript within the round brackets to indicate the index of a data point, right? So for example, we have n data points, and they all have n dimensions, and we want to group the data points into k clusters, right? It can be more than 2 clusters. So we will initialize k cluster centroids. We pick those points from the n-dimensional space. So the algorithm shown here is that we can select select the centroids from the space directly. So the muse does not necessarily is from the original data sets. We are not selecting data points, but some versions of k-means may select randomly sample the k data points from the existing data points, which is also acceptable. Okay, so we will repeat until converge for the body of this function for the procedures within these curly brackets. And first, for all the data points, we will assign it to a cluster by choosing the um, by finding the centroid that is closest. So this argmin means that we find the j that minimize the distance from the current data points xi to the target centroid mu j. Okay, and this distance can be Euclidean distance or can be other types of distances. So anyway, this is the coloring step. We will assign the data points to the closest cluster j. Okay, and the second for loop, it iterates over all the centroids, right? It iterates over all the k centroids by by assigning new values to mu j. And the new value for mu j is the results of computing the mean of all the currents, all the data points within the current cluster, right? So for the cluster J here, for example, we will only use the data sets that are belong to the cluster J. And this function one, so this function one is the indicator function. It equals one if the expression with the brackets is true. Okay. So yeah, so these mathematical expressions or formulas are just a fancier way to describe the process we have shown in the previous slides. And usually speaking, the Euclidean distance is the most common way to compute the distance. So if we want to describe the targets, so use the language from machine learning to describe the k-means formula, then the k-means will minimize this cost function. We want to minimize the distances from the data points to the clusters that the current data points belongs to. And we can, in mathematics, we can prove that this using to minimize this cost function will be guaranteed to converge. So so that's why k-means is one of the most commonly used methods when we want to when we want to discover some patterns within unlabeled data sets, because it's easier to implement. And nowadays we have a lot of efficient implementations in Python in different languages. And it also is guaranteed to converge, which means we can always find some patterns after running the algorithm. Okay, so let's look at some commonly some issues within this utterance. So first, some technical issues and theoretical issues. So first, we need to initialize the centroids. Right. So the method we introduced so far will pick can randomly pick k data points as initial centroids, and sometimes the different initialization will result in different clustering results. Okay, so for example, um, if we have like uh, this is 9 data points, if we pick the red points, the yellow point, and the blue one as initial centroids, then probably after we uh, run a k-means, it will result in 3 clusters. Then what if we choose these 3 data points, the red, gray, yellow, and the blue? It may result 3 clusters of different shapes. So that means the initialization, the way how we select keys really matters to the results. Okay, so how to minimize the ambiguity or to minimize the uncertainty within the results of running k-means is to run multiple times, but with different initializations, and then we evaluate the different resulting clusters. Okay, so we will talk about how to evaluate the results from the clustering algorithm in later slides. And more importantly, there's an improvement to k-means, which is called Kmeans Plus. Let's look at this method first. So Kmeans Plus basically introduces a better way to initialize. So it will choose one centroid uniformly at random from data points. Okay, it will choose one data point at a time. So for each, after a centroid is chosen, for example, then for each data point, we will compute the d of that data point, which is the distance between that data point xi to the nearest centroid that has already been chosen. Okay, so the distance method will be distance value will be updated each time after a new centroid is chosen. But the technical part is that when we choose one new data point as a new centroid, the probability needs to be proportional to the distance. Okay, so the farther away data points will have larger probabilities, which makes sense because we don't want all the clusters, all the initial points to be very close to each other. And if we choose these very close data points as initial points, then the results could be terrible because they don't spread out across all the data points, right? Then the shapes of the clusters would be very strange. So we will use these steps to find the k initial centroids, and this probability being chosen is proportional to the distance from the existing centroids. We'll make sure that the initial centroids will scatter across all the data points as farther away as possible. Okay, so for example, after the first centroid U1, mu1 is selected, then we will have higher chance to select mu2 among these data points because they are farther away from mu1. So it is likely that mu2 is appeared over there. And after mu1 and mu2 is appeared, then we have higher chance to choose mu3 among these lower right parts, or among these lower right points, which is a reasonable way to choose centroids because it's aligns very well to the intuitive observation on the data sets. Okay, that's the problem. That's the issue of initializing the positions for all the data points, for all the centroids. And the second issue that K-means face is that how do we choose K, right? So in the example we use, it's obvious that there are two clusters in the data sets by observing it. But in some cases, it's hard to choose K because sometimes the pattern is not clear. For example, here, if we use two initial clusters, initial centroids, let K equals 2, then the algorithm will always converge. It always converges to two stable clusters, but it may be not a good result. So for the example on the right, if we use three centroids, then it will also converge, but the result is very bizarre because it's quite obvious that there are only two clusters. So it doesn't make sense if we select three clusters. Okay, so it comes to the problem of defining what is a good clustering result. So there could be some systematic evaluations to evaluate to say judge whether a good clustering how a good clustering result looks like. So a good clustering algorithm is basically should make sure that the data points that are similar to exist to appear in the same cluster. And the data points that are of low similarity should appear should be assigned to different clusters. That is our basic principle. And we want a good class. We want an algorithm to automatically follow this principle. So people invent the so-called silhouette coefficients, which is a computational metric to evaluate the quality of a clustering results. So it's a very simple um, quantity computed by using it's a ratio of two numeric to real number, and we have b and a. So in this case, the silhouette is between -1 and 1, and we want to pursue high silhouettes coefficients. So the a here, lowercase a here, is the um, within distance clusters, within cluster distances. So it's the mean distance between the data points and all the other data points in the same cluster. Or put it in a simple way, we can call it a within cluster distance. And B is the between cluster distance. So it is the mean distance between the data points and all the other data points in the next neighbor cluster. Okay, so we want the data points within the same cluster to be as small as possible, and we also want the data points um, with in two clusters should be to be apart. So these silhouettes can be used to measure, to evaluate how good the result is. Say, if given these patterns, the data points on the right here, right, we have basically um, one, two, three, four clusters. Okay, so say if we let the k-means to let the k to be true, and after we run the k-means algorithm, we will have two clusters, and the silhouettes coefficients can be found here, and we see that a large proportion of it is this proportion of data points have pretty low silhouette scores. And if we use the if we use k equals 4, which makes more sense intuitively, right? And then we will see that there basically the overall silhouette score is higher. So this part is above the same threshold, and this part is also above. So here we didn't show a general um, um, the comparison, direct comparison of the values, but we can see that if we use k equals 2, then at least for the cluster 0, it is not a good result because the majority part is pretty low, has pretty low silhouette score. But for the if we use k equals 4, then for the resulting four clusters, they all had a better within a better score, better silhouette scores. Okay, so that is the evaluation for the clustering algorithm. Okay, so let's look at the uh, k-means from my overall speaking. It has pros and cons, so it's easy to implement, and also it's scaled very well to large data sets. Okay, and the cons is also disadvantage is also salience. Like we need to choose k anyway, right? We need to decide the k, and it's not that straightforward, not that intuitive. So we need some hints, and we need some maybe need some a lot of intuitive observations to decide the k, and the k is not always leads to doesn't always lead to a satisfactory result. Okay, and more critical disadvantage is that k-means does not work well on the spherical or convex clusters, right? So like this top example, we have two rings, and we maybe we wish to let the algorithm to decide maybe the inner ring is one cluster and the outside ring is one cluster, okay? But the k-means does not uh, do this, capture this pattern because the underlying uh, k-means actually relies on the underlying mechanism relies on the distance, right? So for example, the data points here is data points, it is closer to the outside ring, right? And relative speaking, these the left half on the inner ring is farther away from these right points on the in the outside ring. So the algorithm is not smart enough to recognize these red points. They are actually connected to these blue points within the same ring. The algorithm is not based on the connectivity, but it's purely on distance. So that's why the spherical or convex clusters, they are not recognized. So we will need alternative methods rather than k-means. Okay, so we will look at a second type, which is called hierarchical clustering. Okay, so the idea is that it will make sure the nearby data points end up in the same cluster. Okay, so compared to k-means, it focuses more on the local distance rather than the global distances. So it will focus on the nearby data points. So the implementation actually relies on some data structure like disjoint sets, but we'll focus on the procedures rather than the implementation details here. So we'll need initialize a collection of clusters. So first of all, after we given the new data sets, we will assign each data point into a cluster, into a collection, into a cluster, which is called CI. So now what we will do is to repeat until there's only one cluster left. We will find a pair of clusters that is closest in the current collection. Okay, we will find the CJ, CI, and CJ that has the minimal distances among all possible combinations of I and J. Okay, so that is a very large uh, amount of computation because we need to search among all the collections, all the clusters thoroughly. And then we will merge the two clusters, C and CJ, CI and CJ, into the new cluster, which we called CINJ with within the superscripts. And then we need to remove the old clusters because they are now merged, and we will add this new cluster into the set. Okay, so these three steps will be repeatedly done until there's only one cluster, because eventually we can connect all the data points into one cluster. Okay, but don't worry, we will remember all the merging step. Remember all the merging step where we add an edge between the two clusters. So the results will be a dendrogram, which is basically a hierarchical tree of clusters. Okay, so this because we are also measuring the closest distance, we need to choose the two clusters that are closest towards each other. So in terms of closest distances, there are multiple ways to define a distance, because within the cluster, there are multiple data points. Then how do we decide the distance? Well, we can use the closest data points or the farthest data points, or the average distance within two clusters. So we'll see some discussion later. Anyway, let's look at a demo, animation first. So for example, we have such many data points from A to N. Okay, so these are single data points. So let's find the closest data point, the closest clusters at the beginning. So they are just A and B. Okay, so we will merge the sets A and B into one set and remove A and B alone. Okay, we put the new set into the collection. So we look at this place, we have the connection between A and B. So this is the first drawer within the dendrogram, the tree path. So the next one will be C and D because they are closest. So we will draw this connection between C and D. The next will be K and G. Okay, we see K and G are connected. Okay, as you can notice that the passes, they appeared at a higher step, right? They appear at a higher step because this is the level of granularity we will define when all the process is done. So basically, the lower passes, the connections at the lower level, they defines higher granularity. Okay, so next will be LLM, find, okay. And the next step, we connect B and D because these sets, the two sets, the set of AB and the set of CD, they have the closest distance among the rest of the clusters. And that's why they are connected in this iteration, in this step, B and D. So if we connect B and D, which means we need to connect two clusters, right, from AB on the left and CD on the right. Okay, so we draw the trees from the with a bottom-up style. We draw the lower level first, and then we gradually grow the trees. So the next one will be J and H. The next one will be A and G. So E will be connected to the cluster in ABCD. And the next one will be HI. HI will be connected. And KI, LN, FD, FL. Okay, so now almost all the clusters, they are connected. So after the N and G, they are connected, then we will have only one cluster left. So at this step, we can claim that, okay, we have finally have a one cluster, which is meaningless because we need more fine-grained separation among the data points. So what we can do is that we will go several levels above the root level. Okay, so we'll choose some threshold that is below the root node in the dendrogram, right? If we choose the root node, then there's only just one cluster, which is not what we want. We want several different clusters. So for example, we use a red dashed line to indicate our threshold, and we uh, remove all the connections that is above the threshold, right? If we remove all the connections, then the result will be what? 4 clusters, right? Because we remove the connections between F and D, F and L, and N and G. So the result is 4 clusters with only F as an isolated data points. So that is one possible way to cluster the data points. And as we can see, the way we set the threshold determines the resulting clusters, right? We can also, um, for example, choose a different cluster. This time we move the threshold a little bit higher, then fewer connections will be removed. Only the connection between F, L, and the NG are removed. So the results will be 3 clusters. So you may think of that this makes more sense, right? Because the F is included in the nearby cluster. But we'll need to use some evaluations to kind of quantify the results of the cluster. So anyway, we can use a moving threshold to obtain different clustering results. If we want fewer clusters, we can move the threshold above to a higher level. If we want fewer clusters, if we want more clusters, then we can set a lower threshold so that more connections are removed. So that is the um, hierarchical clustering example we have shown here. So like we use a more extreme, lower threshold, and more connections will be removed. So the results will be more messy, will be more smaller clusters. Okay. So we mentioned that the distance, there'll be a lot of different choices. So for example, when we consider the distances between clusters, we can use the closest pair of data points, or the farthest pair, or even the average pairs among all the data points. Okay, so that will be different choices of distances will influence the cluster results. For example, if we use the average distance, the dendrogram will be results like this, or farthest or closest, they will be in different results. So the distance is some hyperparameters that we can tune, that we can choose to in order to obtain different types of clusters. Okay, so the pros and cons for hierarchical clustering is also quite clear. So first of all, it is more informative than k-means. Okay, so it's based on the closest distances within existing clusters. And it shows the relationship between clusters, why some clusters are formed in this way, and how a new clusters can be decomposed into several clusters. And also, it's easier to decide the number of clusters. We can simply, after we run the complete clustering algorithm, we can choose different thresholds to decide, immediately decide the proper selection of number of clusters. But cons is also there. It's very slow to compute, right? Because and its time complexity is the cubic function. The reason is also simple because we need to compute the distance between any pair of clusters, basically, right? And after each time the new um, after the new data points, after the new cluster is merged and inserted to the collection, we need to update all the distances. So this really cost a lot of computation time. And it's also sensitive to the initial states of the computation. And it's sensitive to the outliers because it tries to connect all the data points, right? As long as there are data points in it, it will consider the distance between that data points to all the uh, existing clusters. So that is also a cons of k-means. because we consider all data points in the existing data sets. Anyway, we have some improvements over K-means so far. Although the spherical data, the two rings, can still kind of not be ideally recognized, the two patterns, right? But the convex shape, the two U shape, can be successfully separated. So this is something that we want to see, okay? And it also gives us some idea that because the K-means use the kind of the actually the K-means and the hierarchical, they both maintains the distance between clusters, and the difference is that the K-means will compute the distance between all the centroids, between all the data points globally, but mm, the hierarchical cluster algorithm relies on the local distance between two selected um, clusters. So there's some local connectivity information involved in hierarchical clustering, or we can say that the local connectivity information has been placed higher weights compared to K-means. In order to solve the spherical clustering problem, we'll need a algorithm that puts more weights on the local connectivity. So that's why the density-based clustering is proposed. Okay, so this the third type of clustering algorithm we will cover today. So it's a clustering based on the density, which is on the local clustering criterion, which also means the number of densely connected points. And a most well-known implementation is called DBSCAN. Okay, so we'll use DBSCAN as an example today. Okay, so it's proposed in 1996, and basically it's classify all the points into three types: either the core points, or reachable points, or outliers. And the outlier is sometimes also referred to as noisy data points. Okay, so a core data points is defined if at least there are that many minimal points, that many points that are within a distance epsilon to that data points p. Okay, so these mean points can be integer numbers like 5, 6. So if, for example, if there are more than 5 points that are epsilon distance away from p, then p is a core point, and this epsilon is a maximum radius. Okay, so that's how core point is defined, purely on local distance. And a point q is directly reachable from p, then if q is within the distance and p must be a core point, then we say q is reachable from p. Okay, that also makes sense, right? As long as it is within a distance epsilon. And we can draw a path if, for example, p2 is reachable from p1 and p3 is reachable from p2, and until we reached pn, then we can say that pn is also reachable from p1. And all the data points that are not reachable from any other data points are outliers. Okay, so using these criteria, we can basically separate or like group the data points that are densely reachable towards each other into one cluster, and the data points that are not belong to any clusters as outliers. For example, in the figure here, if we let the minimum points to be 5, okay? So for example, use the green points P as center, we draw an epsilon, use the epsilon as a radius to draw a circle. Then of course we can observe there are more than 5, there are way more 5 points and within the circle. So the P is a core point. And Q, if we draw a circle along Q, then there are only 3 points within the circle, within the radius. So Q is not a call point. Okay, but Q may be reachable from P because if we draw a circle along these points, it may include Q into the radius. So there can be some path from P to Q. Okay, so let's look at how DBSCAN actually implemented implemented. So for example, we can set a minimum points to be 4. So all the red points within this demo here are call points because they are reachable from one another. Okay, so they are kind of mutually reachable. So they can form a single cluster. And the points B and C, they are not call points, but they are reachable from A. So in this sense, they can also belong to the cluster as well because they are reachable to the cluster A. But the point N is an outlier because it is neither a call point nor a directly reachable data point. Okay. So in the next few slides, we have a more complete example. Okay. So the DBSCAN will start by finding the points in the epsilon neighborhood for every point. And then we will first identify all the data points, okay, that have more than minimum points neighbors. And then we will find the connected components of core points and ignore all the non-core points. So the connected components is a term in graph data structure. So we will say that a bunch of or a set of vertices in the graph are connected towards each other. Then we say if they are mutually reachable from each other, then we say they are connected components. And we will assign a non-core point to a nearby cluster if it is reachable. Otherwise, it will be a noise. That is the basic 3 steps of the DBSCAN algorithm. So for example, now let's use a even simpler simpler demo with minimal points equals 3, okay? So for example, we start from P1, we draw an epsilon circle, with epsilon radius, then we can find that P1 is a core point, right? So now we can create a new cluster. Let's call it number 1, cluster 1. And the 4 neighboring points, they all become the candidates to expand. Say we expand from P1 to P2, and P2 is also added to the cluster number 1. And we find a new candidate, P3. If we move to P3, and we found a new candidate, P4, but this time it cannot be a candidate because P3 is not a core point. Okay, so we will stop at P3. So we move to the other side, and P5 is a core point so it's added to the cluster. And P6 is added, and a new candidate P7 is found. But P7 and P8 is also found. But P7 is also a core point, okay? And P9 is found, and a new candidate P10 is found. But P10 is not a core point. Now we will stop expanding, okay? So all the rest parts will be the P11 and P12 will be annotated as the noise points. So it's basically decided by the distance between, decided by the number of neighboring points with the current data points as a center and the radius of the epsilon, and that will decide whether the current point is a core point. If yes, then it is part of the current cluster. If it is not, then we will see whether this is reachable to a core point. Then if yes, then it will also belong to the current cluster. Okay, so that's how we draw the cluster 1 among all these data points. Okay, and the pros and cons. Okay, first of all, it's pretty fast. So it's purely based on the local connectivity, like the local distance. And the time complexity is n times log n. And this is associated with the graph algorithms of computing the connected components. And it can find arbitrarily shaped clusters, which is good for us, like the spherical, the convex halls, the convex shapes, they all can be found. And it's also robust to the outliers. So it's recognized as, they are recognized as the noise vectors, noise points. But it cannot work well if the density varies in different regions of data, right? So we need to, because some clusters, they are uh, pretty far away, but they still show some kind of clustering patterns. The only difference is that it has a very low within distance. It has a very low density, but we cannot deny the clustering patterns because of the low density, because the density can change among different regions. Okay, so the epsilon needs to be properly selected. Okay, so the DB scans can solve the spherical example here, and the U-shape convex shape is also no problem. Okay, so yeah, that's so much for the three types of clustering algorithm today. So one common place is that each data point is assigned with a hard clustering label, like whether it's red or whether it's blue. And that is useful when we want to make very clear distinctions. We want to distinguish all the data points with different clusters, but also its disadvantage is that it allows for less ambiguity. But sometimes ambiguity is something we want, because each data point can belong to different categories, but just with different probabilities. So that's something we will talk about in the mixed Gaussian model in the next lecture after the Thanksgiving break. So yeah, that's so much for today. And I will publish the assignments for K-means and for the PCA analysis. All right. Questions are welcome. And I wish you have a wonderful winter break, actually Thanksgiving break. Thank you for coming.